This is the part 2 lecture of modern physics based on HSTR. This video belongs to the HSTR series where I am teaching physics, maths, chemistry and biology. The link of all the videos posted till now in my YouTube channel will be given in the description. So please do go and check out my YouTube channel and please watch the videos and let me know your feedback. Hi friends, welcome back to my YouTube channel Unfog with Dr. Athar Parveen. In our previous lecture, we discussed modern physics based on HSTR Karnataka syllabus. We discussed atoms, constituents of atoms and their properties, atomic mass, mass number, and nuclear fission, fusion and their applications, followed by nuclear chain reaction. And also we discussed the concept of isotopes, isotones and isobars with examples, and we discussed many multiple choice questions to have clear idea on these concepts. In this lecture, I am going to finish the second part of the syllabus, which will be radioactivity, meaning elements which possess radioactivity, alpha decay, beta decay and gamma decay, and half-life and mean life period problems. Okay. And the third part of the syllabus that which includes the atomic models and binding energy and mass energy relation, that I will take in the next part. With that, I will conclude the chapter modern physics. So basically, I have planned 3 parts for modern physics. Okay. And this is the second part. So let us start our class. In our previous class, we discussed all about nuclear chain reaction. What we learned there? We learned that when a uranium-235 is bombarded with a neutron, then that uranium will get splitted into barium and krypton along with 3 neutrons, and lot of energy will be released. This process, it will go on continue and a chain reaction will happen. We discussed that this reaction, it will initiate its own repetition, means it will repeat by itself, and then this nuclear chain reaction, it will occur when the output of nuclear reaction will cause more nuclear reactions to occur. Again that nuclear reactions output, again it will cause more nuclear reactions to occur. That's why that name nuclear chain reaction was there, right? We had given example also that one neutron, it will strike the uranium nucleus and it will cause a fission event. This will release more neutrons. And these excess neutrons, they can go on to cause more fission events to occur. That's why we called it as a chain reaction. And we also told that this nuclear chain reaction has a big advantage because it is used in a nuclear reactor. You don't have nuclear reactor in HSTR syllabus, friends, but believe me, when you learn about nuclear chain reaction, it is important to have at least a little bit idea about nuclear reactor. So, I am not going to explain you working of nuclear reactor or its advantages or what is the phenomenon behind it. Nothing I am going to explain. Only I am going to discuss few 3 to 4 points based on nuclear reactor which may be asked in your exam. Okay, simple points. See, we now know that in nuclear reactor, nuclear chain reaction is going on. Now, it has a few components. I am not going to discuss all components, only 3 or 4 main components I will discuss here. I have displayed the figure also here, and this figure is not complete. Okay, I have displayed only half figure of nuclear reactor, which is important for you. You can see that this reactor, it is having control rods, coolant, moderator, fuel is there, correct, and one steel pressure vessel is there, and one concrete shield is there. That's all. So much. Now let us see the components. These components only we will discuss about them. First, core. Core means you can say that the steel pressure vessel only, that is only core. It contains all the nuclear fuel and it will generate all of the heat. What will be the nuclear fuel here? It will be uranium. Usually it will be uranium, right? So this is the function of the core. Next comes the coolant. What is this coolant? What is the function of this coolant in the nuclear reactor? It is the material that passes through this core, and its function is to control heat. Whatever heat is liberated, see, in a nuclear chain reaction lot of energy is released, right? If lot of energy is released, then heat is also there, isn't it? Energy means heat only, right? So that heat, it will be transferred to some turbine kind of thing in the nuclear reactor. This is done by coolant. Now this coolant, it could be water, it could be heavy water, it could be liquid sodium, helium, or it could be something else also. But examples are this, water and heavy water, you can say. Usually we also use water as coolant, right? See, if we are giving a hot milk to the child doesn't drink much hot milk, right? Child drinks some warm milk. What we do? We take one bowl filled with water and we put the glass of milk in that water and we rotate that glass for a few minutes, right? So that the milk will get cooled and we will give it to the child. That means the water, it acted as a coolant. It took the heat from the milk and it transferred it to the atmosphere, or maybe it absorbed and that water became hot. Okay, the heat gets transferred from the glass of milk to the water. So this is the example for a coolant. Same work it will do in the nuclear reactor also. Next component is the moderator. As the name only indicates, moderator, it will moderate, means it will slow down the neutrons which are produced in the chain reaction by fission. Okay, so that if they slow down the neutrons produced by the fission, they can sustain the chain reaction, means they can control the chain reaction for longer time, they can use it. Next are the control rods. These can be inserted into the reactor core and the reaction rate can be reduced. Means if you insert them in that core in the nuclear reactor, you can reduce the reaction. If you remove it from the nuclear reactor, you can increase the reaction, the fission reaction. So you can control this nuclear reaction by using control rods also. Now we are telling that moderator is also controlling nuclear reaction and control rods are also controlling the nuclear reaction. But there is a difference. What we told, control rods will control the nuclear chain reaction by absorbing neutrons, but a neutron moderator, it will control the nuclear chain reaction by reducing the speed of neutrons. Okay, this is the difference between moderator and control rods. Basically both will control the speed of the nuclear chain reaction. Okay, so these are the points which I wanted to discuss with you all. I am not going into much detail. I am not explaining you the working. I am not telling you to understand the diagram, nothing, because they have not given in the syllabus, right? But because we are learning chain reaction, we should know at least little bit of information regarding nuclear reactor. Now based on these points only, I will give you few multiple choice questions. Believe me friends, these points are very important from Hstr point of view. Okay. The first question is, a nuclear reactor is a device to produce nuclear energy with the help of. Now we know it nicely, right? It is a controlled chain reaction. That nuclear fission or the nuclear chain reaction, that only happens in the nuclear reactor, right? So the nuclear energy can be produced using the nuclear reactor by the help of the controlled chain reaction. Next question. What is used in nuclear reactor as a cooling method or cooling device? Of course, it is the coolant. It is used and its function is to remove the heat released by fission. So option A will be the right answer. Next question. Which part's function is to reduce the energy of fast neutrons to thermal neutrons in nuclear power plant? It should be moderator. Wherever the speed of neutrons is reduced means moderator. Okay. Neutrons are absorbed means control rods. So much you can remember. Next question. Name the moderator used in the nuclear reactor. Like we told that coolant is water, right? Like that only moderator could be graphite. The material which is used as a moderator in the nuclear reactor is graphite. Okay. Next question. Control rods are made of cesium, cadmium, tin, gallium. Control rods, they are usually made of cadmium. Not only cadmium, they can be made of boron or hafnium also. Okay, any three materials can be used to make control rods in a nuclear reactor. Next question. Graphite is used in nuclear reactor as a lubricant, fuel, insulator, reducing the velocity of neutrons. Of course, reducing the velocity of neutrons. That is what we called as moderator, right? So the same answer and the same question they have twisted and asked here. Okay. Next question. See, these questions, no, some 2-3 questions, I think 3 questions are there which can be asked as a general knowledge question also. I am giving it here because we are talking about nuclear reactors, right? Okay, the question is, which of the following is the oldest nuclear research reactor of India? Oldest nuclear reactor. It is Apsara. Remember this name, Apsara. This is the oldest nuclear research reactor of India. Next question. Nuclear energy is generated by nuclear fission and its expression was proposed by Einstein. Then again fission they are telling, then the scientist name they are given Rutherford. Then they are telling fusion. Fusion though it is not the option at all, right? The option nuclear energy, nuclear reactor, nuclear fission is only there, and the expression is given by Einstein. Because in the last lecture I explained you how that energy mass relation is there. E is equals to delta mc square. How this energy is converted, I told you, right?
Indira Gandhi was the Prime Minister of India, and they named that nuclear test as a smiling Buddha.
Okay. Next question. What is the code name of India's first successful nuclear test? This is very famous actually. First nuclear test was conducted okay, so this is a very common question. Usually they ask this question in GK or they may ask in physics also because it is related to nuclear reactor, right? Okay. Let's move on to our next topic, radioactivity. Now radioactivity directly they have given in our syllabus of HSTR, so we have to learn it, right? Now what is radioactivity? It is one spontaneous process. It is one immediate process. Here emission of radiation is happening, that is happening spontaneously, but that radiation is in the form of particles or high energy photons. Okay, this radioactivity is also resulting from some sort of nuclear reaction only, but in this nuclear reaction whatever the energy is released, no, that is in the form of particles or high energy photons. Okay. Now this radioactivity, it is exhibited by few matters, not all matters, means all substances do not exhibit radioactivity. Few matters will exhibit radioactivity, and these matters they emit energy and subatomic particles. What are those subatomic particles? We'll discuss. Later we'll discuss. Now let's talk about radioactivity. Now, why is this radioactivity happening? It is happening due to the nuclear instability of an atom. Okay, this also will discuss elaborately. First, let us know this interesting fact that how this radioactivity was discovered. Actually, a scientist named Henry Becquerel, he discovered radioactivity by accident. Intentionally he did not discover, it was by accident. He was doing something and he landed up finding the radioactivity. What happened was this element uranium, this compound of uranium, it was placed in a drawer containing photographic plates. Now they wrapped it in a black paper and they kept it in that drawer. In that drawer only photographic plates were there. Later, when the photographic plates were taken out for experiment, means when they examined this photographic plate, it was found that those photographic plates were exposed. Exposed means some light was falling on them. Okay. This exposure gave rise to concept of radioactive decay. Okay. Now nothing was there in the drawer. Nothing else was there. Uranium was there and photographic plates were there. Now from where that light will come? It should come from uranium only, right? So that's why they concluded that there is some decay happening in the uranium. The decay was called as radioactive decay. Okay. Now let's talk about the subatomic particles. I told that radioactivity is some spontaneous emission of radiation, right? Either radiation you say or high energy photons you say. Correct? Or subatomic particles are released you say. Those subatomic particles are known as alpha particles, beta particles, okay? Or it could be gamma also. So the decay, they gave different names. When alpha particle was released, they told alpha decay. When beta particle was released, they told beta decay. When gamma particle was released, they told gamma decay, like that. Now in alpha decay, that alpha particle is released, they are telling, no, that alpha particle is nothing but a helium nuclei. Okay, means if in a radioactive reaction, if helium nuclei is released after radioactive decay, that reaction is known as alpha decay. In the same manner, if electrons are emitted from that particle, then that reaction is known as beta decay. Or in case no particles are released, just high energy photons are emitted, then that reaction is known as gamma decay. Okay, I'll give you the nuclear reactions. You will get more idea here. See, in the first reaction, that we are telling mother nucleus to the actual radioactive substance. Okay, means before radioactivity is happening, that actual radioactive substance is the mother nucleus. It will have certain mass number and it will have certain atomic number. Now after radioactivity decay is happening, that mother nucleus will emit alpha particle, and that alpha particle is also coming out from that mother nucleus, right? That's why the remaining nucleus is known as daughter nucleus. Basically, mother nucleus after radioactivity decay will give you one daughter nucleus along with helium. This helium will have mass number 4 and atomic number will be 2. Okay, this helium is known as alpha particle. And the speciality of this alpha decay is that the daughter nucleus came out, right? The daughter nucleus atomic number will be reduced by 2 and mass number will be reduced by 4. Okay. Now don't ask madam what is atomic number and what is mass number. You must watch part 1 of this lecture. Then only you will understand whatever I am discussing today. Okay friends. I'll give the link in the description. Please first to watch part 1 lecture. Then only come back to this lecture. Okay. So I was telling that in daughter nucleus, the mass number will be reduced by 4. Reduced by 4 with the original mother nucleus. Okay. For example, if the mother nucleus had a mass number 10 you say, then daughter nucleus will have 10 minus 4. Means 6 will be the mass number, like that. And atomic number will be reduced by 2. Correct? Next comes the beta decay. In beta decay, electron is emitted. Okay. That electron, it is, you can call it as a radiation, right? That is emitted. And here the daughter nucleus mass number will not change. Atomic number will increase by 1. Okay. Atomic number will increase by 1. Then in gamma decay, the daughter nucleus will be as it is as mother nucleus even after radioactive decay, because here only gamma rays will be emitted. Gamma rays are nothing but high energy photons. No particle is released here. That's why daughter nucleus atomic number and mass number will not be changed. In the first two process, the alpha decay and beta decay, particles were released, right? alpha particle and beta particle. That's the reason why daughter nucleus atomic number and mass number were being changed. Okay. Now why this is happening? This is happening because of the instability of the mother nucleus. Now why is that instability happening? That I'll explain you later in this lecture only. But before that, let us learn this alpha, beta and gamma decay. Once again, I'll give you one short summary so that you can learn it easily. Okay. Now in radioactivity, see actually radioactive substance, it is kept like this. I have kept this figure just to give you an idea that radioactive substance, it is preserved in a lead shielding actually. Okay. Now it may give you alpha rays, it may give you beta rays, or it may give you gamma rays also. Okay. Now one thing you must have noticed, you can see this reactions here. You must have noticed one thing. Alpha particle is positively charged, correct? Electron is negatively charged. And gamma rays, they are high energy photons, they are neutral, they have no charge. Okay, so much you should remember in your mind. Now let us go for the summary. See, what is alpha decay? If one radioactive element is decaying, then you will have one daughter nucleus and one helium ion, or you can say the alpha particle, correct? Here atomic number will decrease by 2 and mass number will decrease by 4. If it is a beta decay, two types of beta decay will happen. One is where an electron and an antineutrino is emitted, and the other one where a positron and a neutrino is emitted. Okay, see that first part, it is known as a beta minus decay, and the second is known as beta plus decay. Means beta decay are of two types. In beta minus decay, electron is liberated. To compensate that electron, one antineutrino is there along with electron. In beta plus decay, along with the daughter nucleus, positron is released. Now to compensate with that positron, one neutrino is also released. Okay, so much simply. You just have a gist. Don't worry. Only thing is that equation should be balanced. That much you see. Okay. Next is the gamma decay. In gamma decay, what happens? That parent compound, it will get excited and it will give you daughter nuclei along with the gamma ray. Okay. So I hope that you got a good idea about alpha, beta and gamma decay now. Now let's talk about few laws of radioactivity. Means some told rules and untold rules also. Just to take them as points. Radioactivity, first of all, it is the result of a decay of the nucleus. Second point is that the nucleus decay rate is independent of temperature and pressure. Means the speed of the nucleus decay, it is independent of temperature and pressure. You understand, right? Whatever the temperature and pressure will be, it will not affect the speed of the radioactive decay. Okay. And this radioactivity, it will depend upon the law of conservation of charge. I told you while explaining in the reaction, right, the charge should be conserved. Whatever the charge is in your left hand side of the reaction should be same as your right hand side of the reaction. You will have to add in the right hand side. Okay, that left hand side and right hand side charge should be same after adding from the right hand side. That will show that whether your law of conservation of charge is satisfied or not. Every time it should be satisfied. Okay, that is why we say that radioactivity is dependent upon the law of conservation of charge. Next, the physical and chemical properties of the daughter nucleus is different from the mother nucleus. This is very important point. Whatever was the mother nucleus properties, they'll be different from the daughter nucleus properties. Okay. And the most important point is that in radioactivity, every time you will see that either alpha, beta or gamma particles, anything can be emitted. Okay. And the rate of decay of radioactivity substance is dependent upon the number of atoms that are present at that time. Obviously, that is only decay, right? If more number of atoms are there, means rate of decay will become slow. If less numbers of atoms are there, means rate of decay will become faster. Okay. And coming to the units of radioactivity, there are two units of radioactivity. One is Curie, Madame Marie Curie's Curie, and Rutherford. 1 Curie is equal to 3.7 into 10 to the power 4 Rutherford. This is the relationship between Curie and Rutherford. They can ask this question as a MCQ. You have to remember that 1 Curie is equal to 3.7 into 10 to the power 4 Rutherford. Okay. Now, what are the uses of radioactivity? One radioactivity substance is there. It is known as americium-241. It is an alpha particle emitter and it is used in domestic smoke detectors. Means if you have some fire in your home, if that detector is there, then it will ring the alarm. Okay. And then radioactivity is used in sterilizing the medical instruments and to diagnose and treat diseases. Many diseases are there. That I'll tell you again. I'll discuss the advantages and disadvantages. At that time I'll tell you. And then radioactivity is used to produce electric power. Okay. Now if I talk about the advantages of radioactivity, gamma rays, they are used to kill cancerous cells. Okay. That's why they are used in radiotherapy also. Then cobalt-60, this is also one radioactive element. It is used to destroy carcinogenic cells. Means these are also carcinogenic, means cancerous only. They are also, cobalt-60 is also used to destroy cancerous cells. And then gamma rays, they are used in scanning the internal parts of the body. And then gamma rays, they are used in killing microbes which are present in the food, so that food is prevented from spoiling. It can increase the shelf life of that food and it can prevent the food from spoiling. And then you can also find the age of the rocks using radioactivity radiations. You can use this argon content measurement which is present in that rock, and then you can know how much age that rock has. Okay. Now, one or two disadvantages are also there. First is that high dosage of radioactive radiation on the body, it might lead to death. Okay. So it is highly toxic. And then radioactive isotopes, they are very expensive because they are very rare. Main thing is that you cannot find it here and there. They are very rare. That's the reason why they are very expensive. Okay. Now gold, diamond, they are all rare, right? That's why they are expensive. Like that only radioactive isotopes are also expensive. Now let's talk about few elements which are radioactive. I have put the periodic table diagram here. Here you can see that the yellow color elements, they are all radioactivity. Basically elements with high atomic number such as uranium, thorium, radium, they all exhibit the property of radioactivity. But among all of them, polonium is highly radioactive. Okay, polonium. Now I will address the question that why some elements are radioactive or why they are unstable. Basically, why is radioactivity happening in some substances? It is not happening in all substances, right? But it is happening in few substances. But why it is happening? Actually, when atoms of element, they have extra neutrons or protons, it will create extra energy in that nucleus. Means their number of protons and number of neutrons, they are not same. They are different. That's why it will create some energy in that nucleus. This will cause atom to become unbalanced or unstable. Okay, that energy should somehow go out, right? It cannot be inside that. So that energy, when it comes out, we are calling that it is radioactivity. Okay. Now I told that polonium is the radioactive element which is most radioactive, right? Means it is most unstable. Okay, it is most common isotope actually, polonium 210. It is most common isotope with just 84 protons but 126 neutrons. This is abnormally large, right? There is so much imbalance. That's why polonium becomes unstable and it is highly toxic. It is highly toxic means if it will be highly toxic to man if he will intake it. Till then it is not toxic. Okay. And this polonium, no, it will emit alpha particles, means helium ions. Okay, they can ask any point from here as multiple choice question, friends. That's why I'm giving you so many points in radioactivity. Now let's see few multiple choice questions based on radioactivity. The question is, elements exhibiting the property of radioactivity have, of course, they have unstable nucleus. That's what we told, right? Since atomic number of these elements, they are high. First of all, that we should remember. Radioactivity is exhibited only by the elements who have high atomic number. Okay. And they have number of protons will be more in the nucleus, or sometimes number of neutrons will be more in the nucleus. So their nucleus, they will have more repulsion between likely charged protons. Okay, or it can happen with neutrons also. Hence their nucleus will become unstable. And what happens during radioactivity? This unstable nucleus, it will split up into the daughter nucleus emitting the radiation, and the daughter nucleus will be stable. Okay, daughter nucleus will be stable. This you have to remember. Okay, next question. Which element exhibits maximum radioactivity? We know it, right? Polonium. It is a radioactive chemical element with atomic number 84. This was discovered by Marie Curie, Madame Marie Curie, in 1898, who named the element after her country, Poland. Okay, she was from that country. That's why she named that element as polonium. I hope that you all know about Madame Marie Curie, right? She was one of the pioneer in radioactivity. Not only she, her husband also. Okay, if you have time, just Google and see the story of Madame Marie Curie. It is very interesting. I am not telling it here because you people may be preparing for examination. I don't want to deviate from the topic. That's why. Okay, but if you all are interested, let me know in the comment section. I'll surely make one video on it. Okay. Now let's talk about radioactivity decay law. Decay law means one law was given. That law, it gave you the rate of decay. Means what is the speed of the decay of radioactivity. Here dN by dt is equal to minus lambda n is there. Here lambda will be decay constant or disintegration constant of radioactive atom. Don't worry about this formula. The other formula is n is equals to n naught e to the power minus lambda t. This, if you remember, it is more than enough. Don't worry about dn by dt. Okay. Here n naught is number of atoms initially present in it. Okay. And n will be the number of atoms present in the final stage. Okay. N naught will be the number of atoms initially present. And lambda is decay constant or disintegration constant of radioactive atom. So just to remember this formula, n is equals to n naught e to the power minus lambda t. Okay. T is the time. Don't worry. I will not tell you to use this formula also. I have my own tricks. I'll tell you. Let's talk about half-life and mean life. Whenever we read about radioactivity, it is must that we should understand half-life and mean life, right? First of all, time during which half of the number of atoms present initially in a radioactive element decay is called half-life. Means adha. See, if you have 10 atoms initially, the time during which the 10 atoms will become 5 atoms is called half-life. Okay, for that radioactive element. How you represent it? You represent it by T half. Half you write it as a subscript. Below T you write. Okay, the time is T half. This is equals to 0.693 by lambda. Lambda, we know that it is decay constant or disintegration constant, right? From where we got this 0.693 means actually it is a logarithm of 2. Natural logarithm of 2. The half-life or T half is equal to natural logarithm of 2 by lambda. But this natural logarithm of 2 is having one value 0.693, which is a constant. That's why we directly wrote 0.693 by lambda. This formula you have to remember. Half-life is equal to, or the T half is equal to 0.693 by lambda. This is half-life. There is one more thing known as the mean life or average life. This is given by 1 by lambda. Okay, 1 by lambda. If you are given the decay constant in the question, then you can find the mean life or average life just by doing its reciprocal. But if they are giving you half life, then that is also related. Average life or mean life is that T is equal to 1.44 into T half. Okay, this is one formula you have to remember. Small t, or the average life or mean life, is equal to 1.44 into half lifetime. Okay. Now I'll give you one more important formula. This will directly give you the procedure to find half-life of radioactive substance. Capital N is equals to N naught by 2 to the power N. N naught is initial amount, right? But small n, no, it is number of half-lives. Okay? Number of half-lives. I will explain you the numericals, then you will understand. Right now, just you note down this formula. Okay? See, this example I have taken. Question is, calculate the half-life of a radioactive substance whose disintegration constant happens to be 0.002 per year. Means they have given you lambda. Directly you can use our formula that T half is equals to 0.693 by lambda. Just write it down. If you write down, no, you cannot divide these decimals, you'll get scared, right? So better make it approximate. 0.693, you make it 0.7. 0.002, you write as it is. Now in the denominator you can write 2 and you can send 3 zeros in the numerator, right? Correct? Now 2 ones are 2, 35s are will be 70. So 0.35 into 1000 or 350 years. Which is there nearby in this options? It is 346 years. That's it. This will be a right answer. Okay. Next question. If the half-life of 100 grams of a radioactive element is 8 years, then how many grams will remain after 32 years? Means half-life is 8 years. Final years they are asking is 32 years. With this you can find, right? You can find a number of half-lives. How you will find? You have to do 32 by 8. This will give you number of half-lives. Then you can, so many times you can divide it. Half, 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 half. Like that you can do. You will get the answer. Or my trick which I will tell you. I showed you that formula, right? You can apply that formula here. N is equals to N naught by 2 to the power N. This will become N, right? N will be 4. How you got it? Final year by the half-life. Final is 32 years by the half-life, which is 8. You got N is equal to 4. Now you just substitute. N naught is the initial amount, right? Initial amount is 100 grams they are given. By 100 by 2 to the power is small n. Small n is 4. 2 to the power 4. So 100 by 16. Or it will be 6.25 grams. Okay, you can just directly use this formula and you can calculate. Only thing is that first you have to find small n. Okay, how you find that small n? You should know that. See, this is not a formula. I am giving you trick. Okay, this small n is not a formula. Final time by half-life. I am giving you trick to remember. Okay, it can be a formula also. It is not wrong. I am just giving you one trick to remember. But this is not wrong also. But you will not find it in any textbook also. Okay, so small n is equal to final time by half-life. What is the final time given in the question and what is the half-life given in the question? With that you can find small n. Okay, I'll show you another example. You will understand. How many milligrams of tritium will remain after 49.2 years if the starting amount is 32 mg? The half-life of tritium is 12.3 years. So first you have to find small n, right? Calculate small n because final time by half-life, you know that it will be 49.2 by 12.3. You will get small n as 4. N naught they have given in the question. Now just substitute. So n will be equal to 32 by 2 to the power 4. 2 to the power 4 will become 16, right? 16 ones are 16 twos are is 32. That's why 2 mg will be the right answer. Okay. So, okay friends, if you find any difficulty in this class, please do let me know in the comment section, or you can also write to me in the Telegram channel. We have a group also there. If you are new to this channel, please join this Telegram group. I'll give the link in the description, and also please do like, share and subscribe to my channel. Okay, this is the one way you can support me. Okay friends, meet you in the third lecture of modern physics. That I will finish that chapter with that third lecture. Okay, all the best. Bye.